Hi everyone. Watch all of this video because before the end, we're going to stumble upon yet another logical roadblock, a logical difficulty we've never encountered before. Will we ever reach the point where at least logic is sufficient to move forward with confidently? The issue we encounter here is a surprising one. In addition to the logical difficulty, the proof we end with here is itself very difficult to achieve. Mathematics is a minefield. You think you have everything ironed out, it should be smooth sailing, and then in the most unlikely of places you realize that the next step is actually quite difficult. That happens here again today. So look at this. There's a very useful criterion for showing that a set is countable, which exactly parallels the theorem from the last video about finite sets. It is the following. Let B be a non-empty set, then the following are equivalent. 1, B is countable. 2, there's a surjective function from the positive integers onto B. And 3, there's an injective function from B into the positive integers. And note here that this theorem is not only about countably infinite sets. It goes slightly further than that, proving statements about countable versus uncountable. Countable includes both finite and countably infinite. So the first two parts of this proof, that 1 implies 2 and that 2 implies 3, follow very closely the proof from the last video about finite sets, and we'll be able to go through them quickly without much commentary. See the last video for more detailed discussion. It's part 3 where we hit a massive roadblock. But first the two easy ones. So let's assume 1 and prove 2. So we suppose that B is countable, and we're going to prove then there's a surjective function between the positive integers and the set B. So if B is countably infinite, that means that there's a bijection between the positive integers and B. And so part of being bijective is being surjective, so we're just done by definition. So if B is finite though, then there's a bijection from a section of positive integers to B for some n greater than 1. That's just the definition of finite. So then we can extend this to a surjection from all of the positive integers onto B just by extending h a little bit. So we'll define a new function f of I. So f of I just equals h of I for 1 to n, and then for anything bigger than n, we just go back to 1. That's fine. Then it's still a surjection, right? We did the same thing for 1 to n, and then for everything else, it doesn't matter. We've already covered B, so we just send it back to 1, and we're done. Okay. So if we assume 2 and prove 3, so now we're going to assume that there's a surjective function f from the positive integers onto B, and we need to prove that there's an injective function going the other way. So just like last time with finite sets, so we define a function from B into the positive integers where g of B equals the smallest element of the inverse image of the element B for the function f, our surjective function. So just like last time, because f is surjective, the pre-image of B is non-empty, so g is well defined. And furthermore, the map is injective because if B does not equal B prime, then the two sets, the pre-image of B and the pre-image of B prime, are disjoint. Same as last time, because f is a well-defined function, then these two pre-images have to be different if there's only one element. So again, look at the last video to see more discussion about that. And since they're disjoint, their smallest elements are different. Their smallest elements are different, so therefore g of B does not equal g of B prime. That's what we needed to prove. That shows that it's injective. Okay, those were the two easy parts. Let me say one more time. The first two parts of this proof follow closely the proof for finite sets, so I'm repeating it quickly here. If any of it's hard to follow, watch the second video on finite sets where we go over it much more carefully. Now the difficult part, we're going to assume there exists a injective function from B into the positive integers. And we need to prove that that implies that B is countable. So the first thing to do, it seems like this is going to be very easy. If B is injective, there's some subset of the positive integers which is the set that's covered by B, right? So we can just limit the range of G to the subset of the positive integers, which will make this function surjective as well, and then we'll have our bijection. Because we're given that it's injective, if we just throw away everything in the range that isn't hit, then what we're left with will be surjective. So what's the problem with that? That's exactly what we did in the proof of the corresponding theory for finite sets. What is different here? Why could we limit the range with no problem in that proof, but we cannot do so readily here? The problem with what we're talking about doing is, the last time we limited the range of a subset of a finite set. The range of G was a finite subset of integers. Here, though, we're talking about limiting the range to a subset of an infinite set of integers. We don't know yet whether an infinite subset of a countably infinite set is countable or not. If you remember, even last time we actually had to prove that a subset of a finite set is also finite. Before we can proceed now, we need to prove that an infinite subset of a countably infinite set is also countable. This sounds strange, but we don't know anything about subsets of the positive integers. That's the problem. It seems like, well, if z plus is countable, then a subset is going to be countable too. But again, there we go again, sort of thinking it sounds obvious, so it must be true. Sounding obvious and being true aren't the same thing. So the problem with what I just said is that we have not proven that, in fact, a bijection with a subset of the positive integers means that the set is countably infinite. So that's what we have to show. So let C be a subset of the positive integers. Now, if this subset C is finite, then we're done, because finite sets are countable by definition. The problem comes if we're looking at infinite subsets of the positive integers. Are those countably infinite? So proving that an infinite subset of positive integers is countably infinite is where the trouble lies. That's where we have to be careful. So we're going to prove it now, and we're going to prove it as a lemma to the above theorem. So the lemma is that if C is an infinite subset of the positive integers, then C is countably infinite. So again, this is what it seems obviously true, but we need to prove this. Once we prove this, then we'll know that if we have a bijection from B to a subset of Z plus, then that will prove that B is countable. To prove that C is countably infinite, we need to define a bijection H from the positive integers to C. We're going to do this by induction. So define H1 to be the smallest element of C. We know that it exists because every non-empty subset of the positive integers has a smallest element. That's the well-ordering property. So for the induction step, assume that H is defined for everything from 1 up to n minus 1. So then we define H of n to be the smallest element from the set of C minus the image set of the set of integers from 1 to n minus 1. So basically, Hn is the smallest element that's in C that hasn't already been hit by one of the previous H's, okay? So we take everything that was hit by something so far, we take out of C, and then H is the smallest element that's left. So that means that H2 is the second smallest element of C, right? Because H1 was the smallest element, so then H2 is the smallest element from what's left. Then H3 is the third smallest. It's the smallest after the first two have been taken out, and so on. So basically, H orders C from the smallest up. It's like an indexing function pointing to the first smallest, second smallest, and so on in C. Okay, so this set is not empty, because if it was empty, then a function from this section of positive integers into C would be surjective, right? If there's nothing left, if this covers everything, then by definition, there's nothing left over. That means that this is surjective. But if this is surjective, that means that C is finite from the theorem that we proved in the last video, right? That if there's a surjective function like this, that means that C is finite. But we know that C is not finite. It's assumed to be infinite. So this can't be surjective, and that means there has to be something left over in C. Therefore, Hn is well defined because it has to equal something. Okay, so by induction then, we assumed everything up to Hn, and then we defined Hn. So by induction, H then is well defined for all n in the positive integers. Okay, so now what we need to do is show that this function is bijective. That will prove that C is countably infinite, right? If there exists a bijection between the positive integers in C, then C is countably infinite. So to show that H is bijective, we need to show first that it is injective and then that it is surjective. So given some integer m less than n, we can see that H of m belongs to the image set of the set of integers from 1 to n minus 1, because it's less than n and this is everything less than n, right? Whereas H of n, by definition, does not belong to this because it's defined as something that's not in this set. So Hn does not equal Hm, right? Because this one is in this set, this one's not in this set, so they can't be equal. So this again shows that it's injective because we have that m does not equal n, and because we have that if m does not equal n, then h of n does not equal h of m. That's the contrapositive definition of injective. So proving that H is surjective requires just a short series of statements. I'm going to state them first, then we'll go back and try to understand each step. They're all straightforward statements, but each one of them makes you say, wait, why? When you first see it. Okay, before I write down those statements, let me write down how we're going to prove that H is surjective. So let C be any element of the set capital C. We're going to show that C lies in the image set of H. We're going to take an element m from the positive integers and show that H of m is greater than or equal to C, and also that H of m is less than or equal to C, and then that shows that therefore H of m equals C. And that will show, since we're taking an arbitrary element of C and we're showing that there's some element m of the positive integers that H sends to C, that shows that H is surjective. Okay, now the statements of the proof. Remember, we'll go over all these carefully after I write them down. First, note that the image set of the positive integers for H cannot be contained in the finite set of integers from 1 to C because H of the positive integers is infinite since H is injective. Therefore, there's an n in the positive integers such that H of n is greater than C. Third, let m be the smallest element of the positive integers such that H of m is greater than or equal to C. Then for all I less than m, we must have that H of I is less than C. Okay, let me take this one off too. Okay, so this is an interesting moment in this proof. Remember that the point of these exercises is to get ourselves tuned in to the subtleties of mathematical rigor. So after we defined the function, I took a second to examine what it is that H is actually doing, right? To describe in words what H does. It's basically indexing the elements of C from smallest up. If we accept that, then it's obvious that there's some m such that H of m equals C. This is another example of the thing that I harp on frequently, learning how to recognize what is obvious from what only seems obvious, but has not actually been proven explicitly. In this case, looking at the first few elements of the image of HZ+, shows us what H does, but it doesn't really prove anything about H. It's very similar to the problem with counting marbles. We can prove that if a bag has 4 or 5 marbles in it, then it has a unique cardinality by physically demonstrating the number of marbles. But that doesn't prove the same thing is true for a boxcar with 10 million marbles. Our intuition tells us it's true, but we haven't proven it. The same thing is going on here. We're looking at what happens with the first few elements of H and Hn, so it's easy to picture what goes on as n gets bigger, but we haven't actually proven anything. So although it's obvious that for any element C in the set capital C, there must be an element H of m that equals C, because we've ordered C, and now we're just counting up to the element in question, we haven't proven that that works. Just like with the boxcar, it's very difficult to imagine how it might even not be true, but that still doesn't make it a proof. So, okay, let's go through this and see if we can understand it. So let C be any element of the set C. We have to show that C lies in the image set of H. That's the definition of surjective. The function H covers every element of the range of C. That is, for every element of C, there is some element in the domain that H sends to that element. Now, remember what we're ultimately trying to prove here, that capital C is an infinite subset of the positive integers. We're trying to prove that C is countable. Okay, so we pick an arbitrary element of C, and remember, C is a subset of the positive integers. So C is also a positive integer. So then we just take, since C is a positive integer, then there's a section from 1 to C of positive integers, right? And then, so this is going to be finite. So there's a section from 1 to C that's a finite section of positive integers. Now, the important thing about that is that the section from 1 to C is not necessarily even a subset of C. Maybe not. This doesn't have to be a subset of this. C could be the set 50, 100, 150, and so on up to infinity. There's still an infinite number of elements here, right? But the section from 1 to C is not a subset of C. So we're actually looking at something different. We're taking whatever element of C we have, and we're looking at all of the integers up to that number. So the section from 1 to C is finite, we know that. But the image set of H for the positive integers is infinite because we just showed that H is injective. So since the positive integers is infinite, then this has to be infinite too. And so that means that the image set of the positive integers, that this set has to be bigger than this set because this is infinite, that's only finite. So this way of doing this is specifically more rigorous than I would have done it, because I would have thought we have that C is 50, 100, 150, and so on. Then whatever C is, there has to be an n such that Hn is bigger than C. That seems obvious to me. But it's obvious, but it doesn't prove it. So we have to prove it using what we know about these sets. And it gets frustrating to figure out how you can do that. So that's why we're constructing a finite set here. We have an infinite set here. So now we know that if this one's finite and that one's infinite, we know that this set is bigger than this set. We're not here yet, but now we have a set that's bigger than this one. Okay. And consequently, we know that there has to be, because this one's finite and this one's infinite, there has to be some element in here that's bigger than C. Okay? So we don't even know what the actual elements of C are. But now we've demonstrated that we know something about them. There has to be one bigger than C. Because whatever element of C you give me, the section of positive integers up to that element is finite. So there has to be something bigger. Okay. So then there must be an n such that h of n is bigger than C, because we just finished showing that h is injective. Since it's injective, that means that each element of n can only go to one element of C, and there's a finite number of them, So there must be some element of the positive integers that goes to some element of that's bigger than C. Okay, so that was statement number 1 and statement number 2. Because h of z cannot be contained in this finite set, therefore, there must be an n in the positive integers such that h of n is bigger than c. Okay, that's what we just showed. Okay, so then next we say, we've shown that there's some element n in the positive integers that's bigger than c. So now let m be the smallest element of the positive integers such that h of m is bigger than or equal to c. Now again, this is a little bit weird because here I just said that it's bigger than c and now I'm just switching it to bigger than or equal to c. Why? Well, so we know that there's at least one element of the positive integers such that h of n is bigger than c, right? The thing is, we haven't yet actually proven that there is an m such that h of m equals c. We're not there yet. So all we know is right now that there is some n that gets us bigger than c. We don't yet know, maybe c's missed entirely. That's the whole point. That's what we're trying to prove. That's what surjectivity requires. So we haven't gotten yet to the point where there's an m such that h of m equals c. But we know that there's an n such that h of n is bigger than c. So, okay, but so then how do we get to that there's a smallest element such that h of m is bigger than or equal to c? Well, this isn't actually claiming that maybe h of m is equal to c. We don't know. Maybe there is, maybe there isn't. We know that there's an n such that h of n is bigger than c. So let the set capital N be the set of all of the n's such that h of n is bigger than c. Now, in addition, there may be some element k such that hk equals c. Again, maybe there is, maybe there isn't. But whatever this element is, maybe it's bigger than n, maybe it's not bigger than n. We don't know. Because we don't know what order these are in. And this, again, we do know because we kind of experimented with it, but we haven't proven that they're in order. So we don't know that yet. We haven't proven it. But whatever this element is, if it exists, let's add it to n so that we're going to define n as all of the n's such that hn is bigger than c, plus this element k if it exists. Maybe it doesn't, don't care. If it exists, add it to k. So this set n, which is all of these n's plus k if it exists, is a set of positive integers. Hence, it has a smallest element by the well-ordering property. So let m equal the smallest element of n, which we know exists from the well-ordering property. Now again, I'm just going to say it again. We don't know what order this set is in, meaning we don't actually know that k is the smallest element of n. It seems obvious, but we haven't shown it. That's what we're doing right now. So, but we're going to set m to be the smallest element of n. So that makes it the smallest element of z plus such that hm is greater than or equal to c. We don't know about this. Maybe it's one of these n's, maybe it's bigger than c, or maybe it's k, in which case it's equal to c. We don't know, but it's going to be one of those two. Okay, that's what we were doing. That's how we went from hn is bigger than c to hm is bigger than or equal to c. We're not saying h of m equals c, but maybe it does. Now, in that case, then for all I less than m, we must have that h of I is less than c. So notice again the precision involved in getting to this point. We're not making a claim about the order of the elements of C or the order of the image of the positive integers. What we're saying is way more simple than that. And it shows the power of the well-ordering property. All we said is that m is the smallest positive integer such that h of m is greater than or equal to c. That means by definition that any integer less than m cannot have h of I greater than or equal to c, because if h of I is greater than or equal to c, then that I would be m, right? Because it would be an element of n that's smaller than m, but that would make that element m. So we know, therefore, that h of I has to be less than c. So what we've shown, without knowing anything about the order of c, or what the gaps are in c, or anything about c, that if I is less than m, then we must have that h of I is less than c. So, okay, so I hope this shows how really easy it is to slip into thinking something is obvious that you haven't yet actually proven. What we had to do here, all of this stemmed from, we had to create a finite set so we can compare it to the infinite set, so that then we know that there has to be some elements that are outside of the first set of positive integers. And then we can go from there to figure out some more information, all without ever knowing anything about the shape of C. Okay, so we know now that C does not belong to the image set of 1 to n minus 1. Oh, I should have, this is M. So C doesn't belong to the image set of 1 to m minus 1. This is just a straightforward restatement of what we just said. Because for every I less than m, h of I is less than c. And I is in this because it's less than m, but then c can't be in the image set of 1 to m minus 1 because all of this set is less than c, because h of I for every element in here is less than c. So c can't be in this. So since c is not an element of the image set of 1 to m minus 1, it must be that c is an element of c minus that set, right? If c's not in this part of c, it must be in what's left of c. And h of m is defined as the smallest element here. So since c is in this, and h of m is the smallest element of this, then we have to have that h of m is less than or equal to c. Okay, so we showed that h of m is bigger than or equal to c. We showed that h of m is less than or equal to c. Therefore, h of m has to equal c. And that's what we needed to show, that for any arbitrary element of the set capital C, there exists an m in the positive integers such that h of m equals c. That's the definition of surjective. So we've shown that h is surjective. Okay, wow. That was quite difficult, but it was all logically sound. And in fact, making it logically sound is what made it difficult. Separating ourselves from argument by hypothesis, by hypothetical reasoning, and forcing ourselves to prove it is why this became quite difficult to iron out. And the scary thing is always, can we do this on our own? It's one thing to follow in someone else's footsteps, but would it be possible for us to construct a proof like this on our own? I don't know. Okay, so are we done? Have we done what we set out to prove, which is that if the set capital C is an infinite subset of the positive integers, then that set is countably infinite? We have, if we've constructed a bijection between the positive integers and C. But did we? Look back over our construction of this function. Hn is the smallest element of the set C minus the image of 1 to n minus 1. Is there anything about that that makes you skeptical? Or is there anything wrong with that? So maybe pause for a second and think about that. Is there anything weird about this? What in the world is h to the n minus 1? Well, what is h? We're in the middle of defining h. How can we be using h in the definition of h when we haven't even finished defining h yet? This is called the principle of recursive definition. It's different from the induction principle. I said we're going to do it by induction. And that isn't exactly true. This isn't induction the way we've done it before. This is recursive definition. So to define something like this requires us to accept that we can define something recursively, that we accept the idea that something has been defined before it's been defined. Now, fortunately for our emotional well-being, this is not yet another axiom that we have to accept. It's actually possible to prove or to develop the principle of recursive definition using the induction principle. So we actually can prove this lemma using only what we already know, using the induction principle. But doing so is really involved. So we're going to skip it for now, and we're just going to accept, as most mathematicians do, that the principle of recursive definition is valid. But if you would like me to go over it in more detail, I can certainly do so. Let me know in the comments. Okay, this is how math goes. You introduce some new concept, and then a lot of results fall directly out of that, and then suddenly you hit a roadblock, and proving the next step requires you to really stretch your mind to keep everything in order. Then it snaps back to simple again until we hit the next roadblock. At the beginning of this video, it seemed as though infinite sets might be simple. They're just sets that do not have a bijective correspondence with a section of positive integers. But then it suddenly gets weird in the most unexpected place. The implications of what you started with are always where it gets weird. So next time we'll finish with infinite sets. We aren't done with infinite sets yet, because of course, if we're specifying that some sets are countably infinite, there must be other sets that are not countably infinite. What in the world does that mean? We'll look at that next time.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.